So alright, we have been discussing the Gcm model, also the learning process of Gcm, right? And so besides Gcm, we also have different versions of graph neural nets proposed already for learning the representation of the nodes inside the graph, right? Another model we will discuss here is called GAT, or the Graph Attention Network. So from the name, we can see this model is defined based on attention, right? And we have mentioned attention already before for the transformer this section. Then today we'll discuss how to use attention to define the GAT model as well. So GAT actually is another version of GCM. So before we talk about GAT, we want to discuss this Gcm model architecture again as shown here. So according to the formula we defined above, when we learn the representation for a target node, we have to integrate all the neighborhood information together, right, for updating their representations. And the way we do the integration is by summing their representation together. Also, during the summation, we will assign the information from different neighbors with a weight, right? And the weight is denoted by what? It's denoted by the degree or the reverse of a degree of the neighbor nodes. For example, if we learn the representation for the node A as a target node, we have to integrate all the information from the surrounding neighbors B, C, D, E, F together, right, for define its new representation. Now here, if we try to integrate the information from the node C to A, we will assign its embedding vector from HC to HA with the scalar weight, right? Its weight is denoted by 1 over gamma C, right? The degree of C node. So here then we have a problem, right? Because this gamma C is fixed. This gamma C is fixed given the graph, right, structure. Given the input graph, if we have a static graph, we know the structure of the graph will not change anymore, right? Therefore, this weight for the 1 over gamma C, for integrating information from C to A will be the same for different layers. However, actually in the model architecture, because for different layers we can learn different representation HA, HC, right? We know that the HA, HC will be different for different layers, and we have to update them layer by layer, right? However, if this assignment weight is fixed, then we may have some potential problems, because for some of the layers, probably this HC will be important for A, right? However, for some other layers, this HC will be less important instead. We should allow this model to adjust the importance for different nodes, right, in updating these representations layer by layer. In other words, we have to provide some flexibility for the model to adjust the weights from different neighbors in the aggregation process. If so, then this weight, this fixed weight for the 1 over gamma C will not work away anymore, right? Because this one is fixed forever. We want to do the model will have some flexibility for adjusting the weights in the integration. Therefore, we need to introduce another mechanism for computing the weights in the integration instead. Then how can we compute these weights, dynamically, or adjust the weights according to the representations of different layers? We know that when we learn the representation for the target node for the case layer, we know the representation for the node layer already, right? We know the HA k-1 for the node target node in the node layer of the model. We also know the representation of the HC of the node layer as well, right, for the k-1 layer. So therefore, when we further utilize the representation for updating the HA for the case layer, we know the representation for the node layer already. Then, in other words, we know how important this C is to A. We should be able to compute these weights, right? The way we can compute these weights is by attention mechanism. We know that we know HA k-1, we know HC k-1 already. So by fitting the representation to a attention mechanism, we can calculate a scalar as a weight, right, by the attention. Based on the representation of the nodes at the node layer, we can further calculate the attention score denoting their weights in the integration instead. This will allow the model to adjust the weights according to the representation we learned, right? And it provides the model with more flexibility in determining the weights or the importance of different neighbors in the integration process. This is the motivation why we need to consider the attention mechanism in the integration for the graph neural nets. Then let's have a look at how can we define the attention score as we show here. So we mentioned that when we try to learn the representation for a node, we try to adjust the weights according to the representation we learn at the node labels. So we try to introduce the attention mechanism into the learning process. And we also illustrate the learning process by the formula we show here. Like here, if we try to update the RS node in the graph, at the case layer, we try to integrate all the nearby nodes representations into, to integrate them together. We will mention we can assign different labels with the attention mechanism, attention score, right, we show here, which is the alpha ij we show here. Then the question will be, how can we define this alpha ij as attention score? So we can define this alpha ij as attention score by the formula we show here. For example, if we are computing the attention score between node I and node j as we show here, according to their knowing representation at the node level, we can integrate their information together, right? We can integrate their information together for defining attention score. The way we define the attention score is by integrating the hi, this node embedding vector, together with j's node embedding vectors, by fitting them together. So we times hi and hj with a variable w as we show here, and we further integrate this learning embedding vector by the whi, whj into attention function. This is a denoted attention function we define. There are different ways to define the attention function. Can be either based on the attention we define for the transformers, or we can define the attention in another way. Now here we just define the attention by the inner product between two vectors. Because this result will be one vector, this one will be another vector, right? We calculate the inner product as attention scores. This will return a scalar number, the EIG as example. This EIG can be any numbers, right? They can be any numbers, denoting what is the correlation between two nodes based on their learned representations. We know that for the i's node that we have so many different neighbors, right? Therefore, by calculating all the neighbors, the EIG scores for all the neighbors of the i's nodes, then we can fit them further into a softmax function for the normalizations. And finally, we can define the attention score to be alpha ij as shown here. We can ensure that for the alpha ij, for the i's node, the summation of all the j's neighbors, right? The summation of this alpha ij score will sum into 1, right? Because here we have softmax function for the normalization. So here we have the attention scores, which is defined based on EIJ term, together with softmax function. By replacing the alpha ij into the updating formula for the Gcm model, then we can define a new model, which is called GAT instead. So we can write the updating formula for the GAT model by the equation we show here. So inside we still integrated all the neighbors from the i's node, right? So here we still integrate all the nodes inside the i's neighborhood node set. We sum them together. And different neighbors we assign with a different weight, which is denoted by the attention score alpha ij as shown here. So we integrate all the neighbor j's and representations together and for define this i's node representation as we show here. So by this integration, we can learn the representation of the nodes layer by layer inside the model architecture, right? Also in the GAT model, they will also incorporate this multi-head attention mechanism as well. In other words, besides this one copy of the attention mechanism we calculate here, we have multiple copies of different attention mechanisms, right? Now we have this W to be one copy for the attention mechanism. If we have multi-head, like K different heads, then we can define different copies of this W, this matrix, variable for different head of attention, right? So by integrating multi-head attention mechanism together, then we can be able to learn the representation for the i's node by integrating them together. Here we have one operator. Normally we can define the operator as averaging of different multi-head attention mechanism. In other words, by calculating different representation with different heads, and then we further sum them together and to calculate the average, and to return the average as the final embedding vector for the nodes inside the model, right? So in this way, we can define the multi-head attention mechanism for defining the representation of the nodes layer by layer. And we can update nodes representation by this formula we show here, layer by layer, until reaching the last layer of the model. So the representation we learn for the final layer of the model can be further fed to the either node classification or the graph classification tasks for learning the model architecture, right? All the variables inside the model. So in this way, we can learn the embedding vector for all the nodes inside the graph, also learn the model architecture as well. And we can also further utilize them to learn to classify the nodes and also classify the graph instances for learning the models, right? As to the learning process of the GAT, it will be very similar to the GCM as we started before for either node classification or for graph classification. Depending on the task we are studying, we can learn the GAT in different manners. Okay, so this is for the GAT model, and the main difference between the GCM and the GAT lies in how can we define the importance of a neighborhood in the integration process. For the GCM, they penalize different neighborhoods by the degree or by the inverse of the degree for the neighbors. However, for the GAT, they penalize different neighbors or calculate the importance scores by the attention mechanism instead. This is the main difference between them. So compared with the GCM, the GAT is more flexible, and you can adjust this integration weights for different neighbors, according to their representation layer by layer. Okay, so this is for the GAT model. So besides the GAT and the GCM problems, we can also cite some other problems with graph neural network models, and we will illustrate them in the following pages.